All right, so the first example I wanted to go over here, it's going to involve integration by parts. And then just to start, I'm sure that you guys have learned one of these two little acronyms here, LIATE, where we've got logs, inverses, algebraic expressions, trig, and exponents or exponentials. And then so the priority for our differentiation term, whether you do it the tabular method, which we'll go ahead and use here, or you do it the standard u, du, and then v, dv. This little acronym lets us kind of determine which one to pick. Oops. And it goes in this order. So we want to choose logs before inverses, before algebraic expressions, before trig, before exponents. And so in this case, we have an algebraic expression and an exponent. And yep, so I see that some people have already pointed out the integration term is going to be e to the x, making our differentiation term x squared. And what I'm going to do is I'll take this derivative until x disappears, giving me 2x, then 2, then 0. And then over here, we've got e to the x, e to the x, e to the x, and one more time, e to the x. And then we know with the tabular method, we've got plus, minus, plus, minus, plus. And the last thing that we do with this tabular method is we kind of go on our diagonals from the first differentiation term here, and then here, and then here, and then here, making this answer x squared e to the x minus 2x e to the x plus 2 e to the x. And then we've got a 0 times e to the x. So then we just have a plus c. It's a little warm-up problem. If you guys have any questions, is LIATE for you or v? It's for you. So in this case, we have x in the differentiation term, or the d column. So I'm going to put x squared here. And then I'm going to take the derivative to x, making this e to the x, e to the x. And then, yeah, of course, give me 1 second. I'll cover the tabular method a little bit more in just a second. And so what we do when we write our integration by parts like this is I'm going to take these two expressions and put them next to each other or multiply them because our integration by parts formula is given by the integral u dv equals u times v minus the integral of v du. And then we're essentially just going to plug and chug. So circled in red here and here, I have x squared e to the x minus the integral of v and du, making this 2x e to the x. And then you'll see what happens here. If we don't use the tabular method, we're going to have to do integration by parts again. But then ultimately following that, we'll get to this answer. So now to go back into a little bit more detail, can you clarify your question a little bit? Like in general, or is there something specific that you missed?
I got a question.
Uh-huh, go for it.
So these are two different methods to solve it?
Yes.
Oh, okay. I thought they're like they had to do with each other, and I was like wondering like how do these two correlate with each other? But they're just two different ways, right?
Right. So this is the more like traditional way here. This is like a newer way. It's a nice little shortcut. But you kind of need to understand what's going on here in order for this to make sense. Uh, if that kind of clarifies your question, as in determining which. So when to use the tabular method versus when to use the notation method. Good question. So immediately in this question, for example, and I'll point it out every example so we can see. Immediately in this example, we know that x is going to eventually disappear. And so the tabular method makes more sense because we can see that it's just going to disappear to 0, like we have here. Versus in this example, if I were to do this again, right, I would get some expression 2x e to the x minus the integral of some new expression, which then that integral would end up being 2 e to the x. And so you see they're the same way. We get to the same result where we multiply our functions here. The only difference is it's more steps here to get to our final answer here. In what situations would the tabular method not work? Let me see real quick. I did one yesterday. Maybe not. So there are instances where the tabular method wouldn't work, but those are in those examples where you have logarithms and inverses. Typically, what would happen is, and I'm not sure, maybe you guys could clarify. I haven't seen it this way, but maybe it's taught like this now. This is alternatively ILATE. I don't know if any of y'all have seen that, but in the case where you have a logarithm and an inverse in the same integral, and they can be interchanged, sometimes the tabular method just won't work. But it's a pretty rare, like case by case scenario. But typically you're gonna have a function that will follow this pretty well. So you don't have to worry about that too much. In the general sense, the tabular method will usually always work. All right. So I'm gonna get you guys to help me out with this example. This next example here, the integral e to the x cosine x dx. Okay. So do you guys want to see the tabular method or do you guys want to go through the traditional method?
Can we do traditional?
Yeah, of course. All right. So we're going to do u du v dv. And if we use Liate, you're not seeing your writing? Oh,
Yeah,
can you guys still hear me?
Yeah, we can hear you, but we can't see.
Okay, give me 1 second.
Oh,
My iPad crashed, sorry.
no, man, you're done. Sorry. Oh,
Give me 1 second here, guys. Okay, my screen should come back here in a second. Okay, you guys see my screen?
yes.
Okay, cool. Thank you. Sorry about that, guys. All right. So following the Liate method, we are in this area of the acronym. So what expression are we going to use for our differentiation term, for our u?
Cosine.
Nice. So we've got cosine. And the derivative of cosine?
Sine.
Sine.
Negative sine.
Sine.
Very nice, thank you. Okay, and then so our integration term is e to the x. And the integral of e to the x is e to the x. So following the integral of u dv equals uv minus v du, I'm going to substitute in my u and my v. So then I get e to the x cosine x minus the integral of v times du. So then we get negative e to the x sine x. All right. So what's next? What do we do next, guys? We have another integration by parts. So how would I set this part up? I have u du v dv. What is my new u term and what is my new v term? Cool.
Sine.
Negative sine x. Okay, and then this is negative cosine e to the x, e to the x. So now I have e to the x. This is from the first expression minus sine x e to the x minus the integral of minus e to the x cosine x.
Oh, I see.
And then we're going to do this one more time, and then I will kind of emphasize a point here in a second. But if we were to do this again, what would we get? So if I have u du v.
Can we just set it
dv.
equal to the original expression and then like combine them?
You're saying set it equal to like this part here, but flip the sign?
No, the question, the integral of e to the x cos x, that is equal to that of the, can like cancel out the last part of the equation and then divided by the, by two basically.
So you're saying I set this equal to
The whole equation equal to the,
Yeah, the
Saying
whole
this.
line equal
Yeah.
to e to the x cosine x, and then you can
Yeah.
just move the one on the right to the left.
but what happens here? What do I leave? What leaves me here? You're saying
Two,
one?
2 times that integral.
Sorry, I'm not following what you're saying. So you're saying I'm going to move this entire integral to the other side, meaning I would divide, right? I would divide by the integral of e to the x cosine x.
You would add or subtract it to the other side.
Yeah.
So you're saying like subtract the integral of e to the x.
Yeah, but then
subtract the integral on the right, like so,
You
add the one on the right to the left. So
This
it
one?
gives
Okay,
you
I
two-
see.
Yeah, it gives you two.
2 integral. Oops.
No. Negative.
I'll rewrite it in a second. I see what you guys mean now. 2 integral e to the x cosine x equals e to the x cosine x plus e to the x sine x. Okay, so then what do we do from here now?
And then we just divide the whole equation by two, and that's probably our answer. But I have a question.
Uh-huh.
We have a negative on the right side, so I don't know how that's gonna make sense.
You're saying this right here?
No, the one on the inside.
This one right here?
Yeah.
So I
That wouldn't work.
what you could do is you could actually no, y'all are correct. Whoever said it wouldn't work is correct because of the integral, right? So even if you just subtracted e to the x cosine x, right? You just have the integral of nothing, which, so the point I wanted to make with this problem, right, is this is the traditional method. And if we just kept going with, let me clean this up real quick. If we just kept going with this expression, right, it would technically go on forever, right? Because you would get another part that you could do integration by parts from this expression. Now, the difference is I'm going to do the same problem, but using the tabular method this time, di. And remember, we used cosine as my derivative term. And then we used e to the x as my integration term. Right? And then so the derivative of cosine is negative sine x. And we have negative cosine. So there are so the question is, so there are times we have to use the tabular method. I don't want to give you a definitive answer because in the scope of this class, generally the tabular method will always work. But there are instances sometimes outside of this class, depending on your major, where the tabular method may not necessarily work.
I have a quick question.
Go for it.
So when you rewrote the problem, like when you were plugging everything in after you like took the derivative and everything, how did
Here,
I'm sorry?
right here, the first
yeah,
time.
the step under that.
Oh, okay, right here.
Yeah. Why did the negative e to the x turn negative after the integral?
Because of this negative sign. So we set up u times v. So then we just multiply these two statements.
Mhm.
And then we have the integral of v times du. And so we have v multiplied by du. And in this case, we have negative sign. So that's where we
Mhm.
got this negative sign here.
Oh, okay. And then
Yeah.
when you take and then you would take would you take the antiderivative or would you take the derivative of what's after the integral?
So you're saying in this step here,
Mm-hmm.
so this integral expression, that's why we set up another integration by parts, because we have to do integration by parts again, because we have another product of two functions.
Oh, so you just keep on doing it until
Right. So that's why the tabular method, the nice thing with the tabular method is if you have a function like this where it repeats, generally it is safe to cut it off after like 3 expressions. Right.
Okay.
So we would go these two, and then I'll make this a little bit nicer. So we have plus, minus, plus, minus, plus, right? And then so I have this expression times this expression, giving me e to the x cosine x minus this expression times this expression. So then we get plus, because of the negative sign here. There's a negative, I'll put it in green. E to the x sine x, oops, change colors, sorry. And then we have this expression here times this expression here. And then we are 1, 2, 3, so it's plus e to the x cosine x. And then I can stop there. So then I have a plus c. Does that kind of make sense how the traditional method will always work, but the tabular method is a nice shortcut?
Yeah.
Sorry, I have a question. For the
Go for it.
cosine x, the third cosine x, wouldn't that be negative because on the tabular method, the derivative of negative sine x is negative cosine x?
You are correct. I covered that up with my stars. My bad. So here we go. So it's plus, we've got a plus sign, but this is negative cosine there. So then it's a negative, negative e to the x cosine x plus c. That makes sense? Everybody still with me?
Yeah, so basically what you're doing is for the tabular method, you're you're breaking it down until you get a positive.
No, not necessarily. You just cut it. So in this instant, in this sense, right? This chart would go on forever. This chart would go on forever, but it doesn't make sense to just keep adding expressions.
When do we stop?
Right. So like, go ahead.
When do we stop?
Generally, the rule is 3.
3? Okay, after 3. Okay.
Yeah. So
And you're just on the side, you're just finding the derivatives of cosine sine, and then that where the plus and the minus goes from.
right, exactly. But pay attention here. I covered it up with my stars. That's my bad. But this is like, you gotta keep track of your signs on this chart because we have negative cosine here. Yeah. Any other questions on this example before I move on?
This was good. This one was a little harder to understand in class, the integration by parts. Everything else was a little bit easier from 3.2 and so on. Thank you.
Nice. Yeah, for sure. Any more clarification, you just feel free to jump in at any time.
So
had one.
that's our final answer?
This right here?
Yeah.
Yep,
I had a question.
go for it.
So regarding the matching up the derivative and the integrals, is it diagonal or is it straight across?
It's diagonal. Let me write it a little bigger here so I can actually draw the circles. So if I have D, I'll just write like 2. So we've got cosine X, right? And then we've got sine X, negative sine X. And then negative cosine X. And then e to the X, e to the X, e to the X, e to the X. So we're gonna match this cosine to this e to the X, this sine to this e to the X, and then this cosine to this e to the X.
Gotcha. Thanks so much.
Uh-huh. Any other questions? All right, so I've got one more. We're gonna do the tabular method, but I'm gonna have you guys kind of work this out first, and then I'll give you guys the answer. So this one is x to the 4th e to the x over 2 dx. So this one is going to involve a little bit of u sub. Hopefully you guys are feeling pretty comfortable about u sub at this point. So I'm going to pause the recording really quick, and then I will start it over in just a second. If you get the answer, feel free to put it in the chat or say it out loud. All right, so I went ahead and set the problem up. So now what I'm doing is I'm just connecting my diagonals. And so this is the first term in purple. This is the purple line. Then I've got my red line. And then plus, minus, plus, minus, plus, minus. So then minus 16 x cubed over 2. This is the red part here. And then green line from these two. With the negative. And I've got minus 96 x squared e to the x over 2. And then if you wanted to, you could. Hold on. Did I make a mistake, guys? I think I made a mistake. One over 2, 1 over 4, 1 over 8, 1 over 16, 1. Yep, there we go.
For the DI method, I'm just looking at it correctly. So until we get to 0, that's where we can stop our answer.
In this case, yes, because we have an algebraic term, so it does disappear. So there is an end. There's a meaningful end, if that makes sense.
I was doing it the other way. I just want to. Can you show it the other way as well? Just want to make sure I got it right. If you have time.
Yeah, of course.
John R. Bro, your thing is. I don't know if you can have it correctly.
Okay, so
wouldn't your integrals for the EX over 2, wasn't it right with the putting the 2 in front because it's going to toss out a 1/2? So if you took the derivative of the 1/2 EX over 2, it's really going to equal 1/4 EX over 2 instead of going back to EX over 2.
You talking about this term?
Yes, I'm talking about the constant in front of the EX over 2. Wouldn't it be the just the 2 and the 4? Because it's going to be, you're trying to counteract that 1/2 it's going to spit out when it derives.
Oh, you are correct. You are correct. Thank you. Yep. Sorry. Yep. So now I've got 1/2. Hold up, got myself confused now. Nope, I had it right the first time. 2, 4, 6, nope, not 6, 8. Reverse chain rule? No, this is reverse product rule. Yep, so I had it right the first time. Sorry, guys. And just double check, always double check. Yeah, okay. So going back to my colors here, this is 2. These 2 become 16. These 2 become 96. And then we can stop here if that's okay with you guys. Do we all agree? Do we disagree?
I had
For
a
the
question.
96, you
Go for
just
it.
multiplied, right?
Can you possibly go over the integral of e to the x divided by 2?
Yeah, of
Yes.
course. So I've got e x over 2. And then so what I want to do is I'm going to use u sub here. So I'm going to let u equal x over 2, which is really... All right, real quick. Okay, so back to what I was saying. This is the same as 1/2 x, right? So the derivative of this du equals 1/2. So my 1/2 dx. So my dx term equals 2 du. And then so if I plug that into e to the u, oops, e to the u, and then right here is my dx term, 2 du. That's where I get 2e, 2e x over 2.
I mean, we don't have to use the u sub, right? We can just use like the property, I guess.
Yeah, as long as you recognize, and thank you for pausing that part. Yeah, as long as you recognize that, you know, this is going to be the reciprocal of the power basically without x.
Yeah.
You know, you don't have to write. If you're comfortable enough with these expressions, you know,
Mhm.
feel free by all means, save yourself the time.
Yeah.
So yeah, I'll set up the other part. Again, this one gets pretty long, just like the other one. So if we have x to the 4th, oops, 4. Real quick, while I'm writing this out, was it taught differently? Like, did everybody learn the tabular method? Did everybody learn the conventional method? I'm not too sure because I'm seeing a lot of mixed in the group.
We learned both, but he didn't. Our professor, he did it. He tried to do a good job of doing both, but it is especially for the ones with the x to the 4th, and x to the 4th is an easy derivative, but
Yeah.
this one is probably better to use the tabular method, as I can see.
Right. Okay. Making okay. Does this? Yeah, I guess it really depends on, you know, the difficulty of the problem and or how fast you are at calculus. Because, you know, like you guys said, this one takes a second if you do this the traditional method, right? So, okay, so then following our chart here, for the traditional. If V is arctan, You know, that's a good question. I'm actually not sure if I have an example like that.
The only thing I wish though on the homework is they're hard. The problems are really hard, especially in 3.1 and some of the other problems like on 3.2 and 3.3. They require us to use what's it called? Oh, I can't remember because some of the problems are really difficult. Is that gonna be like that for the next math sections we have? Like they're super like algebra based?
Oh, are you talking about partial fractions?
You know, on the web work homeworks, they get really like in class we don't do such problems that are like really hard to like solve.
Yeah, I mean, I guess that's kind of the challenge when teaching these subjects, right? Because on one hand, they want to make sure that you guys get the topics down, you know, but at the same time, you know, they want to make sure that you're actually learning, and the way you actually learn is by doing the harder problems. And so it's kind of like a weird, like unhealthy balance between the way it's done in class. But in my opinion, you know, you can do your homework problems, you can do any test question that they throw at you. I know that those partial fraction ones are pretty bad.
Yeah, that was when I was like, oh man. I was trying to use the distributing and like I almost messed them up a couple of times. But I appreciate it. I'll let you continue. Sorry.
No, you're good. You're good. I'm trying to find an example. Yeah, that's just also, I mean, it's web work, you know, it's not it's not bad. It's just not perfect, you know. So there's when it comes to those problems, they're a little bit limited in the way that they can be structured, just kind of given the way it's written. Okay, so I do have an example. I'll get to that example in just a second. Let's finish this one up for everybody who's asking about the traditional method. So to start, I'm going to have x to the fourth, just like our chart, making this 4x cubed. And then we've got e to the x over 2. So the integral becomes 2e to the x over 2. And then again, the formula is uv minus the integral of v du. So an easy way to remember is I'm going to circle these two, and then I'm going to circle these two. Right, so now I can just fill in with my expressions from my circles. So then I've got 2x to the fourth e to the x over 2 minus the integral of 8 e to the x over 2 x cubed. And then from here, we're going to do the same thing. We're going to have, is that correct? That's correct, right? Yeah. U, du, v, dv. And I'm going to do the same thing. I'm going to set up, in this case, we had 4x cubed, giving me 12x squared. And then we had, yeah, but just not just yet. So I guess one thing I failed to mention is if you're going to use the traditional method, you got to remember that you do have to do this part again. So it might be better that instead of simplifying the expression, you leave the constants alone. So that way you don't forget and then do it later. But you can take that constant out when you're ready to integrate. So I guess it would be better to write it like this. 2ex over 2 times 4x
I have a
cubed.
quick question.
Go for it.
So I see that you put the v as 2e to x over 2. Wouldn't the v be e to x over 2, and then the dv would be 2 to e to the x over 2?
No, because this is our integration term. So we're going to take the integral of dv. The integral of dv is v.
And
Does that make sense?
And I haven't done too many of these, but
Not really. Because like for I understand how we do the u, Because for the u, we're taking the derivative, but it's just the v that's a bit confusing. So the dv is going to be the initial v, and the v is going to be the integral of dv.
No. So remember, your initial integral is always given in the form u dv, right? So the initial this e to the x over 2 is this term, your differential dv. Does that make sense?
Yes.
And then so then what we're doing is we're actually integrating this term, like here, giving us this here.
Okay. Okay, that makes a bit more sense. Okay. Thank you.
Hold on. So Gio, where did I lose you? You said u being the second part of the integral. Where does the 2 come from? The 2 comes from here. So let me get rid of my circles and my red lines. Right? Because again, the integration by parts formula. Okay, so this is why you relying on the tabular method is kind of bad. Because sometimes you forget what the formula actually is. And so when you see it or you give a professor that doesn't let you use the tabular method, dv, right? So I have u and v, so I substitute in u and then v, right? And then I need v du for this expression here. Actually, no, I need v du, and so this is my v, and then this is my du. Did that kind of clear it up? No. So this is the 2 that's in front of this e to the x over 2. That's a part of this v up here. And then this 4x cubed is this part here. And then that's why I said don't simplify this to 8 e to the x over 2. What is it? Sorry, x cubed, right? Because you need these constants for your u's and your new u's and your new v's here. That kind of cleared up.
And then you said this one we have to do twice to get the correct answer, correct?
Yes. Yeah. So you would do,
Wow.
yeah, you would do this part and then the resulting integration by parts, which would be, so the integral here would be 4e to the x over 2. So then I have 2x to the 4th e to the x over 2 minus, and then again, u times v would be 16 x cubed. This time you can simplify because we're not integrating anymore. E to the x over 2 minus the integral of v du, 12x squared, nice. And then you're saying this right here? I mean, yeah, technically, but technically the dx is right here. So it's kind of the same as long as you know that you're integrating with respect to x. So here, same thing, dx. And then this, skipping the algebra, if that's okay with you guys, and skipping that integration by parts again, I'm going to get plus minus, sorry. Yep, plus 96. What was it? X squared e to the x over 2. Yep, that's correct. So this would be my next u. And then this would be my next dv. True. The tabular method is, I mean, it is a shortcut, you know, but if you don't know where it comes from and you don't know why you're using the tabular method, just be careful because, you know, sometimes it can get you into trouble, especially, you know, there are professors that don't let you use the tabular method. So just kind of be prepared.
Can you
It is good to know both. Go ahead.
Can you explain one more time why you circled the negative on the? I get the tablet method out a little better since you've done it. Why did you circle the green part?
Oh, this one here, actually that's incorrect. My bad. So I was just making sure that my signs lined up. But the signs really are connected to this part here. Let me move this table over.
Okay.
They're really
I
on the
get
left
the
side.
multiplication part, and I just I'll have to research to do a little more practice on why do we stop at a certain point instead of going down to 0.
So it depends on the function, right? So like for example, if this was like sine x, right? Like the previous example up here. Where did it go? This one, no. This one here, right? If there is no 0 term, like you never get to a 0 here, and you'll never have a 0
Yes,
here,
that's
right? So
correct.
that's why I was saying just cut it off at 3, right?
Oh, okay.
Right. But in this example, we do have a 0 term,
Oh, but
right?
we don't
So
have to go down there if we don't want to.
exactly.
So we can stop at 3. We can't do it at 2. We just have to stop at 3 because there's
Yeah. And so like in some other examples, like if the exponent in this case was different,
x to the 5. We would do 4.
no, yeah, exactly. So, like you would go all the way down until you have a 0. So
Okay.
like if it was like x to the 7th, you're gonna have a really long function.
I got it. Understood. Thank you.
Yep. Why is it a plus, not a minus? Like here, right here in the table. Before the 96. That is an excellent point. Thank you. Yeah, because it is uv minus the integral v du. Thank you, good catch. All right. So how do we feel? Do we want, oh, I guess I do have that arc sine example, so I'll go ahead and do that one right here. All right. So if I have the integral 6 tan inverse 8 over w dw. In this case, what do we use for u? And what do we use for v?
Can we use tan for you?
The tan would be u.
Is it just tan inverse or is the 6 included?
Just tan inverse?
I think this is just a tan inverse.
Almost. So in this case, we're going to go ahead and include the 6 just to make things a little bit easier. So what happens is we get 6 tan inverse. Oops, I'm going to need more space. Oops. 6. Can we still do it without the 6? Yes. You can do it without the 6, but I think it makes the algebra a little bit harder. Keeping the 6 lets us keep the bigger numbers. And so it's easier to see like how they break down, if that makes sense. You guys will see in just a second. Okay, so now that we know that 6 arctan 8 over w is our u, what is this derivative?
Is it 1 over 1 plus, sorry, 6 over 8?
6 over 8?
No, it's gonna be, 1 second, let me think.
What do we think?
6 over 1 plus e divided by w squared.
You say e?
I mean, 8 divided by w squared.
Almost. There should be some simplification there.
Yeah, in class we didn't do too many of the inverses. But we know that the derivative tan is secant squared, so.
Got you.
Yeah, this one's a little harder. I
6
don't
square
remember.
root 4. Nice. Good job, Alexis. So what she said is this derivative is negative 48 over w squared plus 64. And this comes from chain rule. So I'll walk through that real quick. So if I have arctan 6 arctan 8 over w, and I take its derivative, what is the derivative of arctan?
The
Oh,
screen just frozen.
dang it.
Yeah, same for me. Sorry, Mr. Taylor.
No, you're good. That's my fault. There's something going on with my iPad. I'm gonna pause the recording real quick. Recording.
Substitution.
Go for it. Walk me through it.
U is equal to w squared plus 64.
Uh-huh. So then du equals 2w. dw.
Yes. Or du, yes.
du over 2w. And then let's see. So this gives us the integral of negative 48 w over u times du over 2w. Cancel. This becomes 24. Nice, good catch. So then this expression, like we just found, becomes minus 24, the integral of 1 over u. And then from here, we know what this expression is. So then we get, as a final answer, also substituting in my u at the same step, we get 6w arc tan 8 over w plus 24 natural log of w squared plus 64. Very nice. Thank you to whoever called out the u sub. Saved us a lot of work there. So that kind of makes sense. Do you guys want to see the tabular method now, since we used the conventional first?
Yeah, that was
Yes,
hard.
please.
Yeah, of course.
I'm so confused how you guys got negative 48 over W squared plus 64. I don't get where the 64 came from for some reason. I'm like, how did it? I don't know.
So we have, in this term here, right, we get 6 times, actually, I'll just go ahead and put everything in the numerator. You get 6 times 8 over, W times 1 plus W squared. And then what I believe happens is when you substitute this back, we get a reduction. Sorry, my notes skipped that part because I did the tabular method.
I see it.
Oh, this is maybe, hold on, let me jump to the tabular method. Maybe it'll make more sense where that came from.
Okay.
D, I. Okay, so our differentiation term from the beginning was 6 arctan 8 over W, and our integration term was 1 dW. So then this becomes W. This becomes W squared over 2. The derivative of this becomes, this becomes negative 48 over W squared. Oh, and I'm sorry, that actually didn't clear much up at all. So basically just know that if you were to do this algebra in its entirety, where is it? This one here, rather than this, I'll have this 8 over W. If you were to do this algebra in its entirety, you would get this. Just kind of barring like time. I'm gonna ask that you take my word for it for tonight.
Okay.
And then yeah, and then so we pretty much just do the same thing here. I'm gonna have this. Oh, interesting. Okay, so this is actually a case where the tabular method doesn't work. Because right here, we connect those. That gives us our 6W arctan 8 over W. And then we would have a minus here, and then a plus because of the negative 48. But if I multiply these two expressions, what do I get? I get 48W squared over W squared plus 64. And are those two equal? We know that the conventional method is always going to be correct, right? Nice. Thank you, William. Very nice. So William said the tabular method only works with polynomials. So that's again where the whole Liate using Liate for the tabular method falls apart, because as William said, these aren't algebraic expressions. These are trig functions as our derivative, and we can't take the derivative of 1 because it doesn't really get us anywhere, because it's immediately, it would be 1 then 0, and if you multiply anything by 0, you get 0. Wouldn't chain rule make it? Oh, did I miss a negative right here? Oh, there we go. Thank you. -8. Yeah. So all in all, though, moral of the story, final answer is right here. And in this case, tabular method didn't work because we have arctan and no polynomials. All right. So So I want to make sure that I cover the other topics. So if it's cool with you guys, I'm gonna move on to trig integrals.
Sweet.
And then so the first example we're gonna do is sine of 6x cosine 3x dx. We still good on Zoom? Everybody?
Yes, we
Everybody
can
can
see it.
Okay,
You're
cool.
good.
Cool. All right. So to start this off, what are some of the things that y'all's professors have been telling y'all?
The identities. We have to look if
Like
it.
if it's like odd or even,
Keep going.
the exponent.
Right. So we've got an even sign and an odd cosine. Okay, so what did they tell you?
Pull
How to
out
deal
the-
with this?
Pull out the odd cosine when it's the second term. If it's odd, you pull out one of the cosines and then you set it u is equal to cosine and then
Yeah, you would just split it basically.
yeah.
Okay, nice. So you guys are saying sine of the 6x cosine squared x. Oops. And then cosine
Cosine x and dx.
dx. All right,
And then
go for it.
Yeah.
and then we said
For the evens,
We're not using the half fingers. We're gonna use
yeah, we'll use the
substitution.
1 minus so we're gonna use the identity 1 minus so we're gonna substitute the cosine square x. We're gonna change that to 1 minus sine 1 minus sine square x.
Very nice. Thank you. Very nice.
And then we multiply the sine 6x sine power of 6x to the 1 minus sine squared x.
Oh, so okay, so you went ahead and distributed. Okay, so you're saying sine to the 6x, and then I'm gonna go ahead and do what he said. I'm
Yeah,
gonna distribute.
Yeah, multiply that.
Right.
I don't think it's gonna be like that. It's gonna be like sine. It's gonna be sine. Oh yeah, you're right. My bad. Yeah.
Okay, cool. So, very nice. Yep. So you guys caught on. The next part is gonna be u sub.
oh, this is reduction. Okay. This
No,
makes
not almost. This is we're using this identity. That's like the focus of this problem. Is
okay.
recognizing this identity. Okay, so then like you guys said, u sub. So then what is my u in this case?
Sine x. And then
Nice.
the derivative will be cosine x.
Mm-hmm.
And then
So then dx equals.
u6. Oh, sorry, yeah.
No, you're good. You keep talking.
And then we get integral of u6 u to the power of 6 minus u to the power of 8 du basically.
Nice.
And
All right.
then we just do the basic integral, use u to the 7 over 7 and then minus u to the 8 over 8.
U to the 8 over 8.
Oh, u to the 9 over 9, my bad.
Nice.
Yeah.
No, you're good. Nice. And then substitute. Oh, I don't need this extra
And
integral
then
sign.
plus c on the
Cool.
Mm,
and
Then
then substitute u back.
nice.
Yeah, and
So
then
I
you
get-
put everything back in.
Nice. Sine to the 7th minus 1 over 9 sine to the 9th x plus c.
Yeah, everyone's wondering where the sine 8 came from.
Oh, okay, yeah. So this is
We're using the antiderivative. We're using 1 minus u squared, u6.
almost. So I'm gonna take this expression and I'm gonna substitute in this cosine squared with this identity here. And then so what I get is sine to the 6th x. Oops. 1 minus cosine squared x, not cosine. Sine squared x times cosine x dx. And then I distributed this in. And then where we lose the cosine is here in the u sub step right here.
Yeah. With
We would have
the dx.
Right.
The dx.
Right. Nice. Nice.
So that final answer with the 1 over 7 sine 7x, blah, 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 that would be our final answer, correct?
Right. Exactly.
Okay, cool.
Mr. Chair, my professor showed me we can do sine 7x over 7 minus sine 9 over 9 plus c. Is that still okay too?
Yeah. So the only difference is just for like the sake of like trying to stay within the lines. If I included this in the numerator, I would just have sine to the 7th x over 7. But like it's a little tight for one line, so you
That's how I've
can
been putting it. So
yeah, whatever way you're comfortable with. You feel free to use, like in all things in math, whatever you're comfortable with. Don't change it for the sake of a review. You know what I mean? Cool. So the next one we're gonna do here is why did we use cosine to find an identity, not sine? So like they said, what we want to use is we want to look at the powers. And so we want to look at our powers of sine and cosine, right? And we have an even and an odd expression. So whenever the odd expression is on the right, we're going to use that one to kind of break off a piece of that power. But the way I like to think about it is which one of these gets you to 2 faster, right? Because we need to use a square identity. So if I have n equals 6 and m equals 3, which one's closer to 2? 3, right? So I know that I'm going to break this down into m equals 2 plus, or I'm sorry, 2 plus 1 in this sense. Because when you break them off, you add the powers back together. Or if you were to recombine them, you add the powers back together. All right, next example here. Do we have any questions before I move on as I'm writing this? Feel free to jump in as I'm writing this down. All right. So how do we want to start this one?
So we can split the sine,
Uh-huh.
make it sine 2x times sine x over cosine x, and then make sine square x to is it 1 minus cosine, if I'm not mistaken?
1
is
minus
it
cosine what?
cosine x? Or is it
Almost.
square?
Nice. So real quick for anybody that's confused as to where that's coming from, this is just a Pythagorean identity. And so what I have here is I really have 1 equals sine squared x plus cosine squared x. And we just manipulate the term so that we can isolate one of the expressions we need. And in this case, it's sine squared x. So nice. So I'm going to go ahead and substitute that in if you want to continue.
Yeah, so then we would distribute, actually, hold on. Can we bring the cosine up to make negative cosine -1? Are we allowed to do that?
So you're saying I would have
Yes, yeah.
not quite, because cosine inverse or cosine to the -1 or our cosine is something different. In this case, we technically have secant. If we were going to bring the cosine up, come on, pen. There we go. 1 minus cosine squared x sine x. And I'm not too sure about you guys. I would prefer not to do this one. There is a simpler way. There is does anybody know what that other way is?
Can we just cancel the cosines out?
No.
No?
Because because it's in this parentheses.
Okay.
Yeah.
I mean, one sine over cosine, wouldn't that be tangent?
But this is technically not sine over cosine. This is technically hold on, Gabby, I'll get to your point in a second. So technically you would have tan minus cosine, right? So if I distribute the sine in, I have sine over cosine, and then, oh, I'm sorry, cosine sine, right? And this is also not pretty one.
Yeah. Okay, never mind.
No
I
worries,
don't
no
know.
worries. Using Pythagorean identity. Right, so we did that right here. That's what this step is, Gabby, or Gabriella, right here. I already substituted in sine squared for the identity, using the Pythagorean identity.
We
And then
can
you
do
said
U
use,
sub, right? I'm sorry.
very nice. No, you're good, very nice. That's what I was looking for. U equals, what? What is U?
Would U be cosine x? Or would, right? Mhm.
Yep.
Okay.
So then my du is what?
Negative sine.
Nice. So then my dx equals, oh, there's a dx here.
Mr. Taylor, we can use the other way as well if we don't want to deal with the negative, right?
What are you talking about?
Instead of making it cos u, can we make it sine or no?
No. So what you'll see what's about to happen right here.
Okay.
So dx equals du over negative sine x. And then so when I substitute in dx here, the signs cancel, leaving me with just the negative sign here, right? So now my integral becomes 1 minus u squared over u, right?
Yes.
I'm missing yes, and I'm missing a minus sign here. All right, so now what I can do is common denominator, I can split these apart. So I have negative 1 over u
And U squared over U.
plus u.
Oh,
Do you know where the plus came from? We good on that?
no.
So
No.
the negative sign right here. So that's why this is negative and this is positive.
Oh, you distributed it out?
Mm-hmm. So I
Okay.
distributed it in, so this became negative, this became positive.
Oh, and then you canceled out the U squared with the U at the bottoms. That's why it's just U. Okay.
Right, exactly.
That makes sense. Okay.
So to clarify, just in case, already distributing the negative 1 plus u squared over u becomes negative 1 over u plus u squared over u, which is this here. And then it's just standard integration from here. So if I have, so actually I'll just ask you guys to do this. What is the integral of negative 1 over u?
That's negative ln U, right?
Nice. And I don't know why I keep doing that, force of habit. And then my u in this case was cosine, so then I have negative ln cosine x plus 1/2 cosine squared x plus c. What do we think?
Yeah, this one's easier.
Everybody feel okay about these? This one in particular was a little bit easier. The next couple, I wonder.
Substitution.
What's that? Go for it.
So whenever we have any type of quotients that that rest inside of like an integral, would that typically be our sign to do u sub?
Not necessarily, because there are instances. How I wonder, yeah, give me 1 second, Luis. There are instances where your dx term ends up being like some some expression times du, and then so we would use it to cancel the denominator. So there are examples off the top of my head at the moment. I can't think of any. But the way we kind of recognize, at least this is my thought process on we're going to use u sub here, is I have a cosine squared and I have a sine. I know that the derivative of cosine is sine, right? Or negative sine, sorry. And
So it's
what
how can we cancel that essentially?
exactly? How can we cancel this extra term? Kind of like in the u sub, where you would use it to cancel extra things in the numerator or the denominator. It's the same thing. It's just now we're using trig functions.
Gotcha. All right, thank you.
Mm-hmm. Does that kind of clear it up, Luis? Or you want me to go a little bit more in detail? More? Okay, yeah, so right, our goal is to cancel this term, this one here, because it's the extra outlying term, right? In my numerator, I have a cosine. In my denominator, I have a cosine, but then I also have this extra sign, and I don't want it there because if I choose an arbitrary u, I won't be able to get rid of this no matter what I do. And so that's why we use cosine. Also, if we use sine in this example, right, my dx term would end up being du over cosine, and this would be du over cosine times 1 minus cosine squared x sine x over cosine x. And so now, like, we've just added an extra cosine x here. Does that kind of make sense? And so this, like, we know that we can't cancel our cosines. We need to find a way to cancel this sign. And the only way to do that is with the derivative of cosine. How does the du cancel? So du doesn't cancel. Du becomes our differential term when we get it into u form, right? So there's actually a du right here. And then a du here. That makes sense? I will, if there's definitely going to be more u sub in these next coming examples, so we'll cover it there.
That made perfect sense. Yeah, that's how I've been doing it. Thank you.
Yep, no problem. Makes sense? Cool. All right. So I've got a couple more examples, but we're like getting a little close. Unfortunately, it's like a hard stop at 8:30 today. I have a midterm to take. But so do you guys want to see an example involving tangent, an example where the powers are the same, or an example where we have two different angles but the same trig function?
Let's do an odd one for a tangent, if you can. That would be cool.
Yeah. So
Even ones are a lot easier to compute.
oops, got tan 7x x dx. All right. So this is one of these examples where that notion of, I have an even, I have an odd, doesn't really work in my opinion. The way I kind of think about it is, what can I do to reduce tangent? Because I know that I can get rid of my secants using the derivative. And if that didn't make sense, it'll make sense here in a second. So in this case, right, that wasn't like a trick statement or anything. So what is the first thing? What expression am I going to break off? Am I going to break off a tangent or am I going to break off a secant?
The secant?
I think the secant.
Tangent.
Tangent? Yep. Cool. So here's why. So if I have tan 6x secant cubed x. This also kind of goes away from what I was saying earlier of like getting close to 2. That really applies mainly for sine and cosine. For tangent and secant, it's a little bit different. We're going to be taking advantage of the fact that they're in each other's derivatives, if that makes sense. And you'll see in just a second. Oops, I forgot the tangent. I'll put it at the end. Tan x. So this is this one here is from here. So what I can do is, what are common factors of 6?
3 and 2.
Nice. So what I want to do is I want a tangent squared x cubed, right? These two forms are equivalent. All I've done is I've just modified the powers. And you'll see why in just a second. Do we have an identity for this?
I think so.
Yes.
Do you know what it is?
I'm not sure what it is though.
Is it secant squared minus 1?
Very nice. -1. Nice. Okay, cool. Sorry, guys. Secant cubed x tan x. Okay. So what's the next step here?
You said?
Nice. So thank you, Gabriella. So I'm seeing that u equals secant x. Now let's think about why we chose, secant x, sorry. If I leave off the variables, let me know. I tend to do that when I'm not recording. Secant x. Let's think about why we chose secant instead of tangent. So what is our derivative of secant?
Negative tangent?
Not quite.
Oh.
Secant.
Say it again.
Oh, secant tangent.
Tangent.
So it's secant
Nice.
x, tan x.
Thank you. Dx, right? So then dx, if it's all right with y'all, I'm just gonna write 1 over du. And this is dx. So what happens is now I'm gonna do all my substitutions. I get u squared minus 1 cubed, u cubed, and then if I plug in tan x and then plug in my dx, 1 over secant x tan x, we see
The secant x doesn't cancel out, right? It should be like I think you should pull out secant square x times secant x, so we can have secant x tan x. So it would be du basically.
right, but what did we let what did we let u be?
Secant x.
Secant x.
Right. So this differential term is actually technically written
1 over u.
1 over u tangent x. So this cancels, and this becomes 2.
Oh yeah, yeah.
Okay.
So then we come here, I'm gonna rewrite it. So then I get u squared minus 1 cubed du. And then the next part is to FOIL this expression out. But I will save you guys a little bit of the algebra if that's okay with you guys. When you FOIL this out, you're going to get u squared, u to the 6th, minus 3u to the 4th, plus 3u, oops, nope. Did I get my signs wrong? U minus, this is, yeah. 3u squared, sorry, minus 1. And then one more distribution, I get the integral of u to the 8th minus 3, 6th plus 3 u to the 4th minus 1, or minus u squared. Everybody still following me?
Mm-hmm.
Yep, sounds good.
Cool. All right, and then so now from here, it's just standard integration. So I'm gonna get u to the 9th over 9 minus 3 over 7 u to the 7th plus 3 over 5 u to the 5th minus 1 over 3 u squared cubed. And then substituting in u, my final answer is 1/9 secant to the 9th x minus 3 over 7 secant to the 7th x plus 3 over 5 secant to the 5th x minus 1 over 3 secant cubed x plus c. Is there a trick to foiling? I always have to write it out. Unfortunately, if there is a trick, I haven't found it. I know that there are things like completing the square, but I'm not going to show you that because I'm not comfortable with it. I just do it the old-fashioned way of u squared minus 1. You do this minus 1, and then whatever this ends up being, you multiply this by u squared minus 1. Yeah, so if there is a trick, I don't know it, so I'm sorry.
For the if it's 2 but not 3.
In general, so there is a way.
For the 2, it's a squared plus b squared, and then you go from there. You can use it for the 2. For the 3, it's a little more complex.
Right. Yeah, but there is like a mnemonic way to do it. Like they draw a box. There's like a box like this, and you have your functions. Like you'll have like x squared, and then x or whatever, and then you'll have like x squared here x, and then you basically just like snake your way through the box. But like I said, I don't know how to do it. I'm not comfortable with it, so I'm not going to show it to you guys because I don't want to show you guys wrong. It is much safer to just do this. It takes a little bit longer, but it's always, longer is always safer. Cool. So did we understand that example? That one was a little bit different.
Thank you so much. I appreciate it.
Yep, no problem. I saw a request for something. I'd also like to see double angle problem. So I've got something kind of similar to a double angle problem. Have y'all seen problems like this? I just want to make sure before I throw it at y'all. Cosine 15x, cosine 4x. Have y'all seen problems like this?
I was gonna ask something. Not really.
I know a Russian guy who's pretty good at college.
Huh?
I know a Russian guy who's
No? Okay. Then tell you what.
My professor did one where we had to reduce if it's even numbers.
Are you saying? Because I
for,
do
like,
have one. I
the-
wasn't sure what types of problems y'all. It's like cosine
If you can do that,
sine squared
one's hard.
x. Have y'all seen this one?
Yes, there was a
Yes,
problem.
they did an example of that. Where sine is square and then cosine is square, but then it's supposed to equal cosine square would equal 1 plus cosine 2x over 2, and then cosine square would equal 1 minus cosine 2x over 2.
Right. So we can do this one.
Oh
Just
yeah, that's the half angle one. That one's not too bad.
this one.
What was the other one you were doing? The 15. You're doing
Uh,
cos-
So if y'all haven't seen it, I'm not gonna show it to you guys, just because that probably means that y'all don't have it. So as far as like the half angle example, I don't have one. That identity though is sine x over 2 equals the square root of 1 minus cosine x over 2. And I'll be honest though, in like while I was prepping and stuff like that, I didn't see anything like this. It was mainly this, where we use power reduction formulas.
Okay. Okay. Yeah. Maybe my professor just touched up on it a little bit, but I know he did like reduction and stuff in it. And I'll just look over that another time though.
Well, we do have a reduction, so that's what this one is. This one is going to be a reduction problem. Have you guys seen this one? I won't do it if you guys have seen it. Maybe I can just do it
I
anyways. It's
haven't
up to you guys.
seen them both together. Like sine square was like its own thing, and then it had like x over 2 in the inside and something like that.
Oh, okay, I see what you mean. I know what you mean. So likely then I will cover that one tomorrow. There are a lot of people here, so I'm assuming you guys are going to want to get to like partial fractions and things like that. We still need to do trig sub, so oops, 1 second. If that's okay with y'all, I'll probably cover that tomorrow.
Yeah, it's fine.
Okay.
My exam's tomorrow, so I can just look over it anyways, so it's fine.
What time is your exam?
It's at 5. No, it's
5?
at 4, sorry.
Oh, gotcha. Okay.
Yeah.
Good luck. Find that Friday. I have a little extra time.
Yeah, it's a little weird they're starting on Wednesday, but out of my control. Had the power reduction and the double angle in the homework. Okay, so yeah, let's cover this one real quick, and then we'll jump back and we'll do the other one. So in this case, right, you guys know these identities. You guys know these power reduction identities, right?
Yeah. That's gonna be
Cosine squared equals, go for it.
1/2 1 plus cosine 2x.
Yep.
And then the sine squared for identity will be 1/2 1 minus 2 cosine 2x.
Nice. Very nice. Thank you.
Yeah.
All right. So then what we get here is, actually, I'm just going to write this bigger. We get, I'm going to actually put this term on the numerator so we can see it a little bit better. 1 plus and then common denominator, they're both going to share that 1/2. 1 minus.
That's gonna be 1/4 on the outside, right?
Nice. Yep, so it's going to be 1/4 here. And then so the next thing I do is I'm going to FOIL this. Do you guys want to see that algebra, or can you guys take my word for it?
No, that's okay.
Yeah.
What gives it away that you need to use? So in this case, we don't need to use a half angle identity. We use a power reduction because you use a power reduction in this case because if you were to split off a sine or a cosine, you wouldn't be able to cancel the terms appropriately. And then so like if you used cosine, actually you couldn't use cosine because if I did this, it would be 1 minus sine squared, right? And then taking this derivative, I would now add a new sine term in the denominator rather than canceling the sine, which is my goal. So instead, what I'm going to do is we're using the power reduction formula, which is here, or the identities rather, here. Okay, so jumping ahead, I get 1/4 1 minus cosine squared 2x. All right. And then so what's the next step here? What do we recognize?
We can turn 1 minus cosine into sine, right?
You can
So what
use
happens
the-
when you have the integral of sine squared?
Hmm. I don't know.
So you would, in that case, what you're saying here, I would end up back in this form. If I switch to sine and then did the power reduction again, I would get here. So instead, what I'm going to do is I'm actually just going to use this same identity that I used up here for this term, right? And just pay attention here. Cosine squared x equals 1/2 1 plus cosine 2x. So in this case, I have
It
cosine
froze
squared
again.
2x. Oh, it froze. Dang it.
Yeah.
Should be coming back. Okay, so I'm going to use the power reduction here.
Mhm.
And I'm going to use this one, this identity here. So now what I have is the integral of 1/4, 1 minus 1, oh, sorry, 1/2, 1 plus cosine. And then remember, x, 2x. So now I have 2x. This is 4x. Yep. I think my parentheses are correct. I don't think I need 3. No, I do need 3. Okay, so then what is the next step here?
Wait 1 second.
I'll like partly set it up.
use substitution.
Can you tell me why?
We can we use 1 plus cos for? Oh wait, no, that's not gonna work.
Right, the identity is if it was a sine squared, if that's what you're thinking about.
Yeah, no, it's not gonna work.
Would it be chain rule by chance?
Wait, I have another way of writing this. It's probably gonna be much easier. Can you hear that?
Say that again?
I have another way of like doing this. Can I say that?
Yeah, yeah, what did you do instead?
So 1/4 1 minus cosine square x 2x. The power identity of that is gonna be sine squared 2x, right? And then we take the so
Oh,
we're gonna be using the 1/4 times sine squared 2x, and then we're gonna have sorry we're gonna have, I'm sorry, 1 second. So we're gonna have on the next step we're gonna be like expanding using the the power thing
reduction.
again. Power
Mhm.
reduction again, and then we're gonna be having 1/2 1/4 times 1/2 1 minus cos 4x. And then you're gonna be having 1/8 times 1 minus cos 4x. And then you can pull out the 1/8, so we don't need to take the integral of that, and then you just basically have to take the integral of the 1 minus cos 4x, which is gonna be x, sorry, negative 1/4 sine 4x plus c.
Nice.
Yeah.
Yeah, so both ways are perfectly valid. This way just involves a little more algebra. So thank you, I appreciate that. So for those who may not have caught what he said, like what was mentioned before, using the power reduction identity here, and then you do the algebra to reduce, that gets you to this integral. And then following the integral step, we get 1/8 plus c. If that was mentioned in the intro, I apologize. I might have misunderstood. Or when you were talking about this part, I might have misunderstood. So that's my bad. But I appreciate that. Thank you. Do you know which formulas they're going to give us during the exam? So it'll you guys will definitely get the substitution ones. The trig sub identities, these, I'll write them down real quick if you guys, we're gonna move on to trig sub actually, so.
I'm sorry, wait, before we move on, how did
Uh-huh.
you get x minus 1/4? Where did the x come from?
Right here, the integral of x.
Oh, we took the derivative. Okay.
No. So, the way I did it involved extra steps. This part here
Your
is
screen went black.
basically this. Oh, did I lose you guys again?
Yeah.
Yes, but for a moment.
The back?
Yeah.
Okay, cool. Yeah, so doing it this way actually gets you to the same spot eventually. But all he did is he said, I'm gonna take this and I'm gonna substitute this in for sine squared.
Sine squared 2x.
Sorry, sine squared 2x, thank you. And we use the power reduction formula to get us here. And then so that's where we get this 1.
Okay, but how does that 1 turn into x in the final result?
So if I have the integral of 1 dx, this is really the integral of x to the 0 dx. And then so following the power rule, I have x 0 plus 1 over 0 plus 1. Just giving me
Okay. Okay,
giving me
that
x.
makes sense.
Yeah.
Yeah, okay. Sorry.
No
Mhm.
worries, no worries. Cool. So after all of that, our final answer is right here. All right. I think that's about as much as I can cover for that section. So let's get on to trig sub, and hopefully we can get a lot done in the next few minutes. All right. So for the sake of time, please feel free to jump in. But I'm gonna kind of go and just so we can get at least a couple of examples in this session. So the first one we're gonna look at here is 1 over x to the 5th square root 25 minus x squared. And then so those identities that you guys are gonna get, we have, I'll write it over here. If I have them in the form a squared minus b squared x squared, my x is going to equal a over b sine of x, sine theta. And then the radical expression, this part here, is going to equal a cosine theta. If we have a squared plus b squared x squared, notice the difference in signs here. We're going to have x equaling a over b tan theta, where the radical equals a over b secant theta. And then the last one you're going to need to worry about is of the form b squared x squared minus a squared, where x equals a over b secant theta. And this radical here equals a over b tangent theta. So in the recording, if you're watching the recording afterwards, screenshot that, memorize it, whatever you guys need to do to make sure that you remember it on your test. No, caught the mosquito and I let it go. All right. So back to this example, we are presented with the form a squared minus x squared. In this case, b is 1, so we don't need to worry about it. So if a squared equals 25, a equals 5, And then when we're in the form a squared minus x squared, x equals sine, yes, a sine theta, which in this case is 5. And then so substituting in my, so we've got one more term to worry about, dx. So then if I have dx, I have 5 cosine theta, d theta. We don't need to worry about isolating the d theta just yet. This expression breaks down into the integral of 1 over, and then so x is 5 sine theta. So then x to the 5th is going to be 3125 sine to the 5th theta. And then we know that this term simplifies to a cosine theta, a cosine theta. So then in my denominator, I'm going to have 5 cosine theta, and then my numerator is my dx term, which ends up being 5 cosine theta. We see 5 cosine theta cancels, leaving me with d theta in the numerator. And then simplifying this integral, 1 over 3125 integral 1 over sine to the 5th theta. And so what I can really write this as, oh, I did this earlier. Sorry, everybody, real quick pause. This is a 2, not a 5. If it's a 5, it makes it much harder. So this is a 2. Because what we're about to see is d theta 1 over 3125. Instead of having 1 over sine squared, I'm actually just going to have cosecant squared theta, because the reciprocal of sine is cosecant. So the reciprocal of sine squared is cosecant squared. And if you remember from calculus, the integral or the derivative of cotangent is cosecant squared. So I'm sorry, negative cosecant squared. So in this case, I have positive cosecant. So I'm going to actually go back to a negative cotangent, right? So negative 1 over 3125 cotangent theta plus c. And then the last step here is I need to solve for this theta term because my original expression was in terms of x. So what I'm going to do here is I know that, where did it go? Right here. X equals 5 sine theta. So if x equals 5 sine theta, then theta equals, and then I'll do the algebra down here. I'm going to divide this by 5, giving me x over 5 equals sine theta. And then to get rid of this, to isolate the theta, I'm going to multiply by sine inverse, giving me sine inverse, inverse of x over 5, come on, 5 equals theta. And then I'm going to take this and substitute it in right here. And then to bring the expression down, missed right there.
This one's 3.3. I just came back. I had to eat something real quick.
I think, I'm not too sure. I want to say you're correct.
Okay, 3.3. Okay, thank you.
But this is 1 over 3125 cotangent. And then remember theta in this case equals, oops, sine inverse x over 5 plus c. All right, so I've done the problem. Do we have any questions? I'll pause for questions.
I'm a bit confused how you got, like in the beginning, how you turned, like for x, did you just put 25 square? For x squared, did you just put 25x squared? That's what I meant, sorry.
Oh, yeah. Thank you. It's not 3100, or I made the mistake. It was actually x squared, so it'd be 25 there, not 3100. Good catch. But yeah, so what I did is, for this bottom expression here. Oh yeah, sorry. So I made a mistake in the beginning real quick, just to kind of reiterate. I made the leading power here 5 instead of 2, which just makes it a lot harder to deal with, and we don't get this nice cosine. So it is actually just 1 over 25 cotangent sine inverse x over 5. But back to the question, right here, all I did was substitute in x. And so I have 5 sine theta square root 25, sorry. 25 minus 5 sine theta squared. And then doing this algebra here, this reduces, including, don't forget about this term, but this entire expression reduces down here. And then from there, it's just standard algebra, standard trig sub stuff.
Okay.
Maybe you sound lost. Go ahead. If you have another question, go for it.
Me?
I just want to make sure that, yeah, because you asked the question, so I wanted to make sure.
Yeah, okay. I guess my confusion is just how you got 5 sine then.
Oh, thank you. 25 sine. Sine squared. Because it's 5 sine theta squared. So this is here. You would square the 5 and then square the sine.
Okay. Okay. Thank you.
Yep. All right. Let's see. I'll give you guys one more. I'm hesitant to end it on here. How much do you guys really want to see like partial fractions and improper integrals?
Partial fractions are a little easier to me. This one, I haven't done too many of these. I have to go back. This one's hard. The math, the algebra is kind of tough on this one.
Because I have time for one, maybe 2 more.
Yeah,
My
this
midterm is due
one's
at 12, so
yeah, this one's a bit tough.
Are they gonna be like this on the test with it? I don't mind, but man,
I think
what's
the hardest one you guys are gonna get might be something like similar to what we just did.
And can you go over the a squared? Those are just the identities we have to use to solve this problem, correct? The a squared for the secant tan and the ones you search.
This part here.
Yes.
Yeah, so these are the forms that they're going to be presented in. Right, so like in this case, our problem was presented like this because we had square root 25 minus x squared, right? So this is a squared minus x squared.
Okay.
Right. And I guess it's a little misleading because you have this leading x squared term.
Yes.
So do we have to, I would recommend memorizing them in the off chance they don't give them to you guys, but I can't imagine they wouldn't give it to you. That's just from my experience. I can't imagine they wouldn't give it to you because it's a lot. I mean, those are like, and they're really important. Like if you use the wrong one, the problem's wrong, you know? So I don't think that they're, yeah, I don't think that they're that cruel. I don't think that they're, you know, gonna do you guys dirty.
That one's. We'll
I
work
had
on
a,
those.
I had a question.
Go
Possibly.
for it.
Could you possibly go back to the 1/25 cosecant squared and explain how you kind of got to the final answer? Because I kind of got stuck there.
Yeah. So 1 over sine is cosecant, right? So sine 1 over sine squared is cosecant squared. And then if you remember from this is kind of why they emphasized in calculus 1, really memorize all of your trig derivatives, because if you would just have to recall that the derivative of cotangent theta is negative cosecant, right? And so yeah, if you recognize that this minus goes to the other side, I integrate, and then I get, I'm sorry, cosecant squared. So when you integrate this, you just go back the other way, and the minus sign would go to the other side as well. Make sense?
Gotcha. Yeah.
Yeah. Okay. You can tell me if it doesn't make sense. I can.
I guess kind of how can you explain a bit like moving the negative? I guess that might be one.
Yeah. So again, like we have cotangent theta, right, equals the derivative of this equals cosecant squared theta, negative cosecant squared theta, right? But in this case, or now if I take this integral, right, take this integral here, the integral of negative squared, it's important to just recognize that this expression, including the negative, is cotangent. Right? So if I multiply it by -1 to make it positive, right? All I've done is multiply it by -1. Right? I'm also multiplying the other side by -1.
Yeah,
Right.
so that would make cotangent negative in that case.
Exactly.
Gotcha.
Yeah. That cleared up?
Yeah, we cleared it up. Thank you.
Cool. All right. So you guys would rather do more of the trig sub rather than partial fractions?
Yes, please. Yes, please.
All right. Sorry. Okay, so let me see. I want to make sure there's one that like I will stay a little bit longer. I want to make sure that we at least cover everything we wanna. I have until midnight to do my midterm, so I'm sure I'll have enough time.
Look with your midterm, man. What are you studying, or what do you have to take for your midterm?
It is probability computing.
Oh God.
Yeah.
That sounds well. That could be probably used for in Vegas if you ever do the casinos for the
I'm not gonna lie, I tried when I went to Vegas. It did not work out in my favor. So
How about cards? Cards are a little easier to work with that.
yeah, but they use 6 decks now, and that's too many cards to remember.
Oh God, 6 decks.
Yeah. They've covered up all of their tracks for sure.
That's hard enough.
All right, so where can I find a recording? So as soon as I'm done and as soon as I get the video onto the cloud, I will post it to my personal YouTube channel because that'll be the fastest way to get it onto y'all's Canvas. So probably if we end here around 9, it'll be there around 11. Okay, so the last one I'm going to do here for you guys, this one is kind of a big mix of everything that you guys have done so far, including from like the first couple of units. We've got e to the 4x 1 plus e to the 2x dx. All right, so do you guys see the form that we need to use?
Is it tangent?
You're probably right. Not quite. We have a plus.
Damn it. Okay. That's a 1 plus or is that at
The
1
secant,
e?
isn't it?
Are you saying, yeah, sorry, it's 1 plus e to the 2x.
So it'll be secant?
So you're saying this one here.
Yes.
Okay, nice. Yeah, okay, then that might have been what you were saying with tangent, this one here. If that was the case, then yes, you're correct as well. Nice. So it is in tangent, but here's the issue. I can't just substitute in tangent because of this e. But what I can do is I can let u equal e to the x. Right, and so I'm going to do a little bit of substitution here. So I have u to the 4th square root 1 plus u squared du, and then so du e to the x. And then real quick, my pen will work, dx equals du over e to the x. And then so what happens when I substitute this here, this reduces down to u to the 3rd, giving me u cubed 1 plus u squared. All right, now we can use our identity, right? We're of the form squared, a squared plus x squared. Oops. X squared. And then I'm going to, in this case, I'm going to let u equal tangent theta. So then my du, what is the derivative of tangent?
Secant tangent?
Almost. That's the derivative of secant.
Oh.
Secant squared.
Secant
Nice.
x squared.
Thank you. Secant squared theta d theta. And then so my du, there's a du here, equals du over secant squared. Theta.
Quick question.
Go for it.
How did we cancel out one of the exponents for u? How that went from a 4 to a 3?
So in the substitution step, I'm
Mhm.
going to substitute in dx for du over e to the x.
Mhm.
And then before we convert everything to u's, I'm going to cancel here, and then I'm going to reduce this to a 3.
Gotcha. Okay, thank you. Appreciate it.
Yep, no problem. All right. Where are we? D theta equals, sorry, d theta. Okay. And so now what I can do is I can go ahead and substitute everything that I know. U cubed is tangent cubed. Do you guys remember what this simplifies to?
The tangent cube?
The this part here, the radical.
Wouldn't that just be secant squared?
Group consensus?
You have to do the
I'm seeing
derivative
secant.
first, right?
Okay, nice. All right. Sorry. So then I've got secant, oops, secant theta. Right? Do we agree?
Mm-hmm.
Everybody in agreement?
Mm-hmm. Yeah.
Okay, 1 second. Sorry. So when I substitute in d theta, I get oh, I see. Okay, so remember we have du, right? I'm just going to substitute that in. No need for this here, right? So then I have this secant squared theta, and then getting rid of this because I don't need it, d theta. So then this gives me tangent cubed, theta, secant cubed, theta, d theta. All right, so we did an example pretty similar to this. So the next step here is I want to use tangent to cancel this secant. Now we make tan u. Right, okay, yeah, so you jumped ahead a little bit. So I've got here tan squared theta, tan theta, secant cubed theta, d theta. And then what is this identity?
One plus secant squared. Or secant
Positive or
theta.
negative one?
Negative.
Nice, thank you. Secant theta minus 1. And then we get tan theta secant cubed d theta. Oh, and this is secant squared. All right. So now we're going to do u sub. So then my u becomes secant theta. My du becomes
secant tangent.
nice. Secant tangent d theta. Then d theta. Now we need a d theta term equals du over secant theta tan theta. All right, so substituting in my u's and substituting in my d theta, I get the integral u squared minus 1. Secant tan, it cancels here. I'll make this a little bit bigger.
So then 1 over u.
Here and here. And then so if I divide secant cubed by secant, what do I get?
Secant cubed by secant. Secant squared.
Nice. And then what did we let secant be?
U. So u
Nice.
squared.
Nice. U squared, and then back to du. And then now I'm going to distribute that u squared. Gives me u to the 4th minus u squared du. Take this integral. This gives me u to the 5th over 5 minus u cubed over 3 plus c. Substituting in my u again, I'm going to have 1/5 secant to the 5th theta minus 1/3 secant cubed theta. And then now we need to talk about how do we get to theta. So if we remember from the beginning, we substituted in u as e to the x, right? If you remember, this is our original problem right here. So I substituted in u as e to the x, and I also substituted in u as tangent theta. I'm going to take advantage of this, and I'm going to make myself a little triangle. So if tangent theta equals e to the x, if you guys remember from maybe geometry, maybe pre-cal, tangent can also be expressed as opposite over adjacent. Actually, if you don't remember that little mnemonic, SOHCAHTOA, S-O-K-C over H, then TOA over A. So I know that in my reference triangle here, I am working opposite. So this is the opposite. I'll call this one A. I'll call this one B. So it's A over B. And in this case, tangent theta equals e to the x. So I can write that as e to the x over 1, right? So then A equals e to the x, B equals 1. And then, so we need to find this, we need to find C, and that's found by the Pythagorean theorem. So Pythagorean theorem gives me C equals the square root of 1 plus e's to the 2x. Right? Pythagorean theorem is a squared plus b squared equals c squared. And so c squared is 1 squared plus e to the x squared. I take the square root, gets me here. Okay, nice. So now we have our reference triangle. And then now what we need to think about is the reciprocal of this chart. Cosecant equals hypotenuse over opposite. Secant equals hypotenuse over adjacent. And then cotangent equals adjacent over opposite. Right, all I did was flip the fractions. All I'm doing is putting my reciprocals. And so we made x equal to, sorry, one second. Oh, that's right. Okay, so we're using secant, right? We're using secant in this equation. So I know this, right? I just found my hypotenuse. This equals 1 plus e to the 2x. And so what I'm going to do is I'm going to write secant theta equals square root 1 plus e to the 2x over, and then my adjacent, which is b, right here, is 1. So then secant theta equals 1 plus e to the 2x. Yep, nice, thank you. And then to isolate theta, I am going to take the, no. This is it. So now I have secant theta equals square root 1 plus e to the 2x. And so now the last step is just to substitute that back in here. So I have 1 over 5 square root. I'm going to put this in parentheses. 1 plus e to the 2x to the 5th minus 1 over 3 square root 1 plus e to the 2x to the 3rd plus c. And so after all of that, this is our final answer right here. Any questions?
I just don't get how you go from like a regular equation to then like tangent and then secant. Like I'm still a bit confused from the first problem. Like I don't get that connection.
Where did it go? Where's my little chart? Are you talking about like these forms?
Yeah, I'm not sure how they really plug in. They're a bit confusing.
Okay, so let's take this example again. This one that we're looking at right here. I know in this case x equals a over b sine theta, right? So if I don't look at anything else, I just have x. I'm gonna plug in, and I said this was x squared. Yeah, so I have x in this case is 5 sine theta, right? Squared. And then the square
Yes,
root.
but how did you get 5 sine theta? That
Oh,
It's
okay,
like
so
another confusion.
right here, this is the form that we're presented, right? And this expression, we have A and we have B. Typically, I've seen a lot of y'all's homework, B is just 1, but it is good to know that it's there. We see that when we have our like equivalents for X, we have A right here, and it's just the same A that's under the radical, right? But in this case, we have A squared, right? A squared. So A squared equals 25. So then the square root of A
Oh, so you have to
is
square
5.
root it, so it's 5. Okay.
Right. And then from there, I have 25 minus, and then X squared again would be 5 sine theta squared. And then this expression reduces to 5 cosine theta. And then here we have 25 sine squared theta. And then don't forget, we also had a dx term right here. And so when they plug that in, you get a nice cancellation from the numerator and the denominator,
Mm-hmm.
giving us 1 over sine squared x, or yeah, 1 over sine squared theta.
Okay, that makes sense.
Make sense?
Mm-hmm.
Any
Thank
other
you.
questions about the past couple examples we've done?
I think I had one.
Go for it.
Gotcha. So it kind of goes back to the one we did before this with the cosecant. How do we go from just cosecant to cotangent of the sine inverse? Because that part kind of confused me.
So, oh, okay. So like in this part in the answer.
Mm-hmm.
So what we did is when we integrated cosecant theta, right, we got 1 over 25, or negative 1 over 25 cotangent theta, right? But our original expression is in terms of x, right? So when we started the problem, we have this little relation x equals 5 sine theta. Now what we need to do is we need to isolate theta. And that's what we did down here. So actually, let me erase this real quick, and then I will rewrite the whole statement. If x equals 5 sine theta, then theta equals sine inverse of x over 5 by this. So I have 5 sine theta equals x. I'm going to divide by 5, giving me sine x of sine theta equals x over 5. And then in order to get theta by itself,
we take the inverse.
Right, exactly. So then we get theta equals sine inverse of x over 5. And then we just take this.
And just plug it in place of, so tangent is cotangent is left by itself, but we just plug in the inverse of sine.
Right, exactly. Right. This is theta. This whole part right here.
Gotcha.
Any other questions from y'all?
No, not good.
We'll wait a second, see if people are typing anything. So I guess to close, like I said, this will be posted as soon as I can. It took YouTube like 30 minutes, I think, to post the other video. This one's definitely going to be longer, so it might take a little bit longer for the video to render. I'll make sure that it gets up on y'all's Canvas page as soon as possible. But in the meantime, while y'all are waiting, please, I encourage you guys to go check out that other video I made. I apologize for any of the mistakes or if it's a little rough. Like I said in the intro of that one, I wasn't aware that y'all's tests started Wednesday. I thought they started Thursday. So I kind of made a little last minute review session for those that couldn't make it tomorrow or who already have the test. But it is there for y'all's final, so that's also a decent
It's on
resource.
your YouTube channel?
No, so I put the link on y'all's announcements page and it just goes to my personal YouTube channel. It was just the
Okay.
fastest way to get it to you guys.
Okay, cool. Awesome. Thank you.
And yeah, of course.
We'll be here
Yeah,
for
like I said,
Thursday too, right?
what's that?
We'll be here for Thursday too, or no?
No, not Thursday, tomorrow.
Okay, sweet.
Yeah.
I'll see if I can make it again. Thank you.
Yes, same time tomorrow. No problem. Have a good night if you're heading out.
Yeah.
Yeah, so in the other video, I made sure to cover all the topics. There aren't nearly as many examples. I also don't go too much into depth about some of the processes, just kind of depending on the topic. But if you have any questions regarding that video, please feel free to reach out, before your test. Other than that, if you guys aren't coming to tomorrow's session, good luck on y'all's exams. I know you guys are gonna do great. Like I said, feel free to email me, where can I find the video? It'll be on your announcements page on Canvas. Or not the announcement page, I'm sorry, my TA page, the little module that says TA. Everybody should have one at this point. Yeah, so that's all from me tonight. You guys have a wonderful rest of your evening, and I will talk to you guys later.